Exercise 3E and F, determining transformations in sketching. Today we're learning about determining transformations applied to a function and sketching the transformed function. What you need to be able to do is rearrange the equation in terms of old x and y, determine each transformation applied to old x and y, and then sketch the transformed function given these transformation. So in order to determine transformations, you can either look at the function, which is just the function method, or for more complicated equations, we can use the dash method. So for the dash method, to determine the transformations, we need to isolate new x and new y in terms of x and y in order to understand their story. So what happened to x and y? So what I'm looking for is something like x dash is equal to 2x, which tells me the story of what happened to old x, in that it's been multiplied by 2. So the way that we do this, 4 simple steps. First step is to rearrange the equation to get y and x on separate sides. So everything that's to do with y is on one side, everything that's to do with x on the other side. So that includes pluses, not necessarily plus x, plus 2, anything that might be divided, and so on. So it's like you want two separate lines, y on one side, x on the other. What we do is we equate y and x to the transformed equation. We'll rearrange the equation to get y dash and x dash by itself, and then we can read the transformation. So might sound a little bit confusing, so let's go ahead and just try an example, and I think it'll make a lot more sense. Example 10 says, find a sequence of transformations that takes the graph of y equals root x to the graph of y equals root 2x minus 1. So the first thing that I would do is write out my two equations. This is the old, and to make clear that this is the new, I'm going to put dashes in. So I'm trying to figure out how did I get from this graph to this graph. Now, in terms of separating, so step 1 is we need to separate y and x on different sides. Now, there's actually not much that we can do here because everything on this side is bounded by this bracket. So I actually can't really move anything. If though, for example, I had a plus 2 here, then I would take that over to that side. So anything that is not bound related to x, I would take over to the other side. All right, so that's already done. So I can just go ahead and tick it. It's two separate sides. Now, step 2 is to equate the y side with the y side, the x side with the x side. So this is the y side, and this here is the x side. So y equals y dash, and then I don't need to put the square root because that's exactly the same. I will equate this here. All right, so now that I've equated to the two sides, the third step is to isolate x dash and y dash, because remember what we're trying to do is we're trying to figure out the story, what happened to x and y, the old x and y. So in terms of y, there's really not much I can do here, but for x, what I can do is add 1 and then divide by 2. So that's your x dash there. Now what I can see is that in order to get new y, this is what I need to do to old y, which is nothing. And in order to get new x, this is what I need to do. Now, in terms of the order that you state your transformations in, it's very important to state them in a particular order. So step 4 is to describe. And there's more than one answer here, depending on the way that you express your solution. So in general, we really like to tell our descriptions in terms of these 3 bits of order. So dilations, reflections, translations. But in reality, it's all about what has happened to X first. So what I can see is that in this case, the 1 has been added first. There's like invisible brackets there. And then I've divided by 2. Or if you do want to put it in the order of DRT, what you need to do is separate it. And now I can see that this happened first. First, I divided by x by 2, and then I add a half. Now, if you were to write either one of those descriptions, they would be correct. So it doesn't have to be in this order, as long as it follows the order of whatever you have stated. So it's up to you whether you want to go to there. Either way is fine. Now, I might just leave it as the original one, just so that you can see what that looks like. So here, the first transformation would be a translation. So translate by 1 unit to the right, and then dilate by factor half from the y-axis. Okay, so this is the order that we generally state things in, but it doesn't have to be that way. What's more important is that you follow the order of your transformation. Now, if instead you wanted to use this, that's totally fine. First, I would say that there's a dilation of factor half from the y-axis, then a translation of a half in the positive direction. Both are going to be correct answers, and be aware of that, because when you do your solutions in a textbook, you might not get the exact same one just because they might have manipulated the equation. So I'll rub out this DRT part here because we don't really need that right now. It's just something to keep at the back of your mind if you want to follow that particular process. All right, now that's the first way. It's using the dash method, and I would always recommend this for more complicated equations. Now, the second way is to just kind of look at it and see what happens. And this is something that we should be able to do with more simple equations. Now, uh, again, I'm going to introduce or state this DRT, wrong way. We usually talk about it in terms of dilations, reflections, translations. Now, when we're reading a function, I would always recommend that you do it this way. When it's the dash method, as long as you follow just steps correctly, then it doesn't really matter. But in this case, I would always recommend that you do dilations, reflections, translations. Now, in order to see the true dilations and in order to see the true reflections and translations, what we should always do is pull out any value in front of the x. And then we can go ahead and state what's happened. So because we've just started with a very simple function, we can just have a look at this. So the 2, that would be a dilation. So dilate by factor half from x-axis, and then 2. So this was our 1. Then we've got translate, and remember the sign changes by factor half to the right. Okay, and if you have a look, this solution looks different to the previous one because I went off of this. However, if you were to manipulate your equation, you'd actually get the same. So that's why I've done the 2 different ones so that you can see the 2 different transformations is actually exactly the same. The one thing I would say is that whenever we're stating it in this form, I would always aim for that DRT. When it's in this form, you can absolutely go for DRT, or you can just read it off. Either way works. Okay, let's go ahead and do some more practice. So find a sequence of transformation which takes the graph of this to the graph of that. Now this one's a little bit more unusual because usually we start with the simple and go to the more complicated. Now we're starting with complicated and going to the more simple one. So if you feel confident enough, feel free to read it off. For me, I always prefer the dash method just to make sure I'm not making any mistakes. So that's what I'm going to do. Now, step 1, remember, is to isolate, or to separate rather. Separate x and y for both functions. So this is my old function here, and I'm just going to take everything over. So the 6 can be taken over and the 3 can be taken over. So anything that's not stuck in the bracket for x should be taken over to the other side. So that's y minus 6 divided by 3 is equal to 1 x minus 1 squared. So that's now been separated, all the y's on one side, all the x's on the other. Step 2, oh, actually, I should also write down my new function, which is this one. Okay, step 2 is to equate. So the old is equal to the new, and old equal to the new. Notice that I'm not writing, I'm not necessarily writing out the squares. I don't need it because it's the same. I've just noticed that it's actually not the same because I forgot to put the squared there. Okay, step 3. So step 3 is to get x dash y dash on its own, so to isolate. What you'll notice is that when you go from a more complicated equation to a simple equation, it's already in that form. It's actually already done for you. So usually I'd need to rearrange to get it by itself, but it's already done because it's more complicated to the simple. And then step 4 is to describe. Okay, again, feel free to separate if you like. I'm just going to leave it as it is just for simplicity's sake. So 1, 2, 3. Now, if you started to talk about x and then go to y, so I could totally do 1, 2, 3. It doesn't really matter which one because they're not related. So just start with one variable and then talk about the other. What does matter is the order when you're talking about a single variable. So this one has to be 1, then 2. It can't be 1, then 2. All right, so I've labeled them all out just to make it a bit easier to describe. So this is translate 6 units left. Then we have dilate by a third. I should write it properly, by a factor third from the x-axis because that's affecting the y values. And then the third transformation is to translate 1 unit left, not left, down. Uh, it is left. I made a mistake here. I wonder how many of you picked that up. Y goes up and down, so because it's a negative, that should be translate 6 units down. Hopefully you picked that up. If not, be careful with that in the future. Okay, so that's one solution. If you tried it on your own before, you can also do, I'll just show you the other one. So y on 3 minus 6 divided by 3 is 2. So then you would have dilate by a factor of third and then translate by 2 down. So that is another option as well. Okay, next one. Same idea, find a sequence of transformations which takes that graph to the graph of y equals x squared. So hopefully we can get a little bit faster now. So first step is to separate. So everything that is not bounded by the bracket goes to the other side. And for our new graph, there's not really much that needs to happen. 2, go ahead and equate the two sides. So y minus 6 is y dash. 5x minus 1 is x dash. For step 3, it's to isolate. However, again, because we're going from more complicated to a simple, it's already done. And then step 4 is to describe. Okay, so in terms of steps, doesn't matter whether you start with the y or x. So I'll just go from left to right. So with y, there's only really one thing that's happened, which is that one. And then with x, the 5, then the translation. So it's whatever's closest to x. It's kind of like if you were to do your BODMAS. So multiplying comes before, sorry, not BODMAS, your algebra, SAMDOB, which is the opposite way around. We would consider what is attached to x first. Okay, let's go ahead and describe. All right, we'll go for y. Translate 6 units down because it's negative. Then we will dilate by a factor 5 from the y-axis. And then translate 1 unit down, a unit to the left. Okay, so that should be your 3 there. You could also state these first and then this one next. It doesn't really matter about that order. Okay, moving on to example 11, it says the graph of y equals x squared is transformed so that the equation becomes this. Define the sequence. So same idea again. Let's go through these. So step 1, separate. So this is my old, this is my new, and I'm going to go ahead and rearrange it at the same time. So this needs to go to the other side and this needs to go. So anything that is not bound within the bracket. So plus 4 and then times by 2. Put my dashes in to indicate that that's new. Step 2, that's going to be to equate. So the y sides are equal to each other and the x sides are equal to each other. Step 3 is to isolate. So we're going to rearrange to get y dash and x dash by itself. So I'm going to divide by 2, subtract 4, and then here I will subtract 3 and then divide by 2. All right, and 4 is to describe. So I'm just going to go ahead and number all of the different transformations we have. So first, second, third, fourth. All right, so we've got dilate by a factor 1/2 from x-axis, translate 4 down, translate 3 left, and dilate by a factor 1/2 from y-axis. All right, so you can see that once you get the hang of it, how quick you can go. All right, next one again, say the transformations that have been applied to the first function in order to obtain the second. So that's our second function, it's the new. First thing I'll do is go ahead and put the dashes in. All right, first step, separate. So I need to get rid of the 3 and the negative. So in order to get rid of the negative, I'm going to actually swap the two of these here. So we'll have 5 minus x on 2. I can't do anything with the square root. It's all bounded under 1. And then on the other side, I'll have 3 minus y. And then with this side, just so that I can make the sides match the order, it's root x is equal to root y. 2 is to equate. Actually, I don't need the square root because they both have square roots on it. 3 is to isolate. I don't need to isolate because it's already done for you. So again, when you go from more complicated to simple, it's already sorted out. 4 is to describe. So let's go. So reflection first, that's closest to x. Then this one, this, reflection, and so lots of transformations happening here. Right, so we've got a reflection in the y-axis, translation 5 units to the right, because it's a positive number. We will then have dilation by a factor of half, and that'll be from the y-axis because it's attached to the x. All right, so that's the first lot done. Now we'll talk about the second lot. So again, we've got another reflection. This time it's in the x-axis. And then we've got a not dilation, translation, 3 units upwards because it's positive. All right, so you'll get the hang of it. It just takes a little bit of practice for this. Now, the next one is to sketch transformations. And the idea, I suppose, behind this is that, to figure out what the transformation is, you can do this whole dash method and you can list it all out. So then you can start with the original and then apply this. But it's quite a lot of work, and we don't necessarily want to do all of that when we are sketching. And in fact, we've been practicing for so long how to sketch these types of graphs with the transformations that we don't need to go through this process. So this process, this dash process, is more so for more complicated functions, and it's more for being able to write them out. Now, just a couple of things to remember. Whenever it's attached to the x, it's the opposite. So if it's a -1, then we go to the right by 1 unit. And if we have a number in front of the x, then it's a dilation of the reciprocal. So 2 becomes a half, and it's from the y-axis. The rest should be very straightforward. Okay, so example 13, sketch this graph. So this is a square root graph. This is just what my basic square root graph looks like, and I need to apply my transformations. So I'm just going to read them off. Now, remember the order DRT? It's really important that we apply it when we're reading off the function straight away. So there's no dilations. First, I'm going to reflect, and then I will translate. You can kind of do these at the same time. So we've got a reflection in the x-axis, and then I'm just going to write this shorthand. You wouldn't write this on an exam. So that's 2 units to the left and then 3 units down. So that's just your little notes so that you know exactly what has happened there. Now notice, sorry, that should be to the right. I just said if it's the sign, we do the opposite to it. Okay, other things that we need when we are sketching these kind of graphs are our intercepts and also any endpoints that we have. So what I do know is that this graph has been reflected downwards and then it's gone down. So I'm not even going to have an X or a Y intercept, but what I should find is the endpoint so I know exactly where to start. What I can do is read that from my graph. So if you remember, your general form is x minus h plus k. and your endpoint is at h and k. So in this case, our endpoint will be at 2 and -3. So I think that should be enough information for us to put it onto our graph. We'll draw on my axes now. That'll be x, y. My endpoint we said is at 2 and -3. 1, 2, 3. And then it's just an upside down square root graph. What we do sometimes like to do to show if there are any transformation or like dilation specifically is to put in another point. So I might just put in, trying to think of an easy point. If I put 6, for example, into here, 6 minus 2 will be 4, and that'll give me a nice square root. So when x is equal to 6, y will be equal to 6 minus 2 minus 3. That'll be root 4, which is just 2 minus 3 is -5. So 2, 3, 4, 5, 6. That'll be 6, and we want -5. So hasn't quite gone through the point, which is a little bit annoying. I'm gonna have to draw that again. Probably should have found that before I went ahead and drew it. But there you go. And that's another reason why it's actually worth doing this, to make sure that your graph is quite accurate. Because sometimes in exams, especially when you draw on grids, they actually do check if your graph goes through certain points. So there you go. That's a much better description of what that square root function is going to look like. Okay, last one. So example 14, sketch the graph of y equals 3 on x minus 2 plus 4. So again, D, R, no reflections, T. Okay, so we've got, oops, wrong way, dilation by factor 3 from x-axis. So all that does is it multiplies every x value, every y value by 3. We can't really see it too much when we actually draw it because it's all about the zoom. So the way that we generally show it is by showing a point. And then 2, we're going to go 2 to the right and 4 up. Now, this is really important for this kind of graph because this is a hyperbola. So with a hyperbola, our key points are asymptotes. So usually their x and y is equal to 0. Now that I've moved 2 to the left, that means my x asymptote is at 2 and my y asymptote is at 4. Now, because I've lifted my whole graph up, and a hyperbola, not a hyperbola, a truncus usually looks like this, I'm not going to have any x-intercepts, but I will have a y-intercept, so let's go ahead and find that. So I'll just make x equal to 0. That'll be -2 squared plus 4. So -2 squared is 4, and then 3 divided by 4 is 0.75, or 3/4. The reason I've just gone into decimal mode is just to make it a little bit easier in terms of where it's going to be placed on my graph. Okay, I think that's pretty much everything that we need. So let's go ahead and put our axes in. And we'll also put our asymptotes in. So we have one at 2, one at 4. Just because of the scale, I'll do it. I'll make my y go up by 2s. So this will be x equal 2, and this will be y is equal to 4. And I do know that my y-intercept is also at 4.75 because I'm going up by 2s. That means that should be 5. That means my y-intercept should be there. And now, to the best of your ability, you can go ahead and try to draw your truncus in. Let's see how this is going to go. Yeah, I thought that was going to come a straight line. All right, I'm just going to have to freehand it, I think. That'll have to do. And you just want to try and make it as symmetrical as you can on the other side as well. And see how tricky it is. But hopefully you're off drawing your own one and not worrying too much about what mine is looking like. There we go, something. of that sort. So that'll be 0 and 4.75. Okay, so that's the end of this exercise, exercises 3E and 3F. We'll see you next time.